Okay, hi everyone, and welcome back to my channel in Economist. So, in the previous video, I have talked about what is stationarity of a time series. I have gone into the concepts and also told you why is it important to understand the concept of stationarity. If you haven't watched that video, I would recommend you to see that video first. I'll give the link in the description and then come back to this particular video. In this video, I'll be going into the types of stationarity. Particularly, I'll be discussing what is weak stationarity and what is strong stationarity, right? So let's start with this. Firstly, let us understand what do we mean by weak stationarity. Weak stationarity is also known as the covariance stationarity. Okay, let me write it down. Weak stationarity is also known as covariance stationary, right? Okay. Now suppose you have a time series process yt where t is varying from 1 to n, right? Now when do we say that this process yt is weak stationary or covariance stationary? We will say this process is weak stationary or covariance stationary if it satisfies certain properties. If it satisfies certain properties. What are the properties? These properties I have discussed in the previous, video graphically. Now let us write it down formally. The first property will be the expected value, that is the unconditional mean of this process is independent of the time t, which basically means this has to be a constant, right? The unconditional mean have to be constant. The second property is that the variance of yt is also independent of t, which basically means it also has to be a constant, right? And there is a third property which is the autocovariance of yt, and some lag value of yt is independent of t, but it can depend on age, where this age is not equals to 0. So in a way autocovariance also has to be a constant. Constant basically means a scalar quantity which is independent of time. So this autocovariance can depend on age, that is this lag value, right? It can depend on this lag value, but it has to be strictly independent of t. So all these three statistical properties that we call it has to be independent of t, right? And this will give you your condition for the weak stationarity, which we also known as covariance stationary. And one thing I wanted to share with you is that whenever we talk about stationarity, we generally mean weak stationarity. So in problems also, in solving questions also, whenever you are told to find out the process is stationary or not, you will see that we imply it is weak stationary or not, right? We never generally talk about strong stationarity because it's a very strong condition and it requires many more things to understand. But whenever you are told to find out a process is stationary or not, you will generally consider it is weak stationary or not. So basically you need to check these three properties. Now one additional thing that I want to mention here is that we know when age equals to 0, covariance of yt minus age will be simply covariance of yt, right? This h is 0, so it is yt, and covariance of yt and yt is nothing but variance of yt, right? This I hope you know. It simply comes from the formula of covariance. So expectation of yt minus expectation yt into yt minus expectation yt. So this is basically expectation yt minus expectation yt whole square, which is nothing but the variance, right? So what you can do, you can basically combine these two formulas, right? These two properties you can combine and write it in a compact way. So what are the required properties? What are the required properties? The required properties are as follows. The first property is the same, that expectation of yt is independent of t. This is the same as before, but you can combine the 2 and the 3 property, right? This 2 and 3 property you can combine and write that covariance of yt minus h is independent of t for all h, right? For all h. So here I have mentioned that for h is not equals to 0, because when h equals to 0, this will be the variance, right? When h equals to 0, this will be the variance. That is what I have written here. You can see from here. So whenever h is 0, this is variance, and whenever h is not equals to 0, this is autocovariance. So if you combine this, if you write for all h means h can be greater than 0, it can be equals to 0, it can be less than 0. So for all h, you will say that covariance of yt minus h is independent of t, right? So these are the basically two properties that if satisfies, you will say that the process is weak stationary or covariant stationary. I hope this is absolutely clear to you. Now, knowing this concept will help you in proving a very important result that you will use repeatedly in solving questions. I am doing everything from the perspective of solving questions, right? The ultimate aim of everything is to problem solving, right? So I'll give everything to you that will help you to solve questions and tackle time series problems, right? So for tackling that, you need to know this result, which you will use repeatedly, that for a stationary process yt. So stationary again means the weak stationary here, as I have mentioned that if nothing is specifically given to you what kind of stationarity, you will assume that we are talking about weak stationarity. So that for a stationary process means for a weak stationary process or for a covariant stationary process yt, gamma h is exactly equals to gamma minus h. Gamma h is what? Gamma h is nothing but this autocorrelation. Gamma h is covariance of yt plus h. And what is gamma minus h? Gamma minus h is covariance of yt minus h. So these two expressions will be absolutely same for all values of h, which is h is when h is greater than 0, equals to 0 or less than 0. So basically, again, we are saying the same thing in a different way, that if you consider these three time points, right? Tth time point, t plus h time point, t minus h time point. The statistical property in terms of autocorrelation function will be the same, right? So if you take the covariance of yt in this time point and yt in this time point, the autocovariance in these two time points will be exactly similar to yt and yt minus h. And when this will be true? When the process is stationary. So you can understand this intuitively also. I have mentioned in the previous video that for stationarity, the statistical properties will not change, right? For stationarity, the statistical properties will not change over time. And one of the properties was the autocovariance. In the statistical properties that I have mentioned, one of the properties was autocovariance. So if you consider the covariance between these two and these two time points, the value of the process in these time points, so that will be the same, right? But you have to formally prove it. So let me do that proof for you. How will you prove this? So let's start from the gamma h. What is gamma h? Gamma h is covariance of yt plus h, right? Okay. Now what you will do, right? This yt can be written as yt plus h minus h, right? Yt can be written as yt plus h minus h. This will ultimately cancel out and give you this. And the rest parts will be as it is. Yt plus h is the same. Now, what you will do, assume t plus h is equals to some t prime, right? So this t plus h, and here you have t plus h. Assume this t plus h to be some t prime. So what you will get, covariance of y t prime minus h, and here you have y t prime, right? So you're just replacing t plus h by t prime, you have this. Now from the property of covariance, what is the property? Covariance of AB equals to covariance of BA, right? This is the property of covariance. So if you apply this to here, what you will get? This will be covariance of yt prime will come first and then yt prime minus h. I've just, reversed swap the arguments here. This to this and this to this, right? AB is BA, same. So these two things are same. And can you guess what is this? Covariance of yt prime minus h? Yes, you got it right. This is simply gamma minus h. Why this is so? Let us see this expression. Gamma minus h is covariance of yt minus h, right? And here what you have? Covariance of yt prime minus h. Now how do you justify this, that t prime is equals to t? It is given to you that yt is covariant stationary, right? Yt is covariant stationary, which basically means that all the statistical properties you consider for the time point t will be exactly equals to the properties that you will be finding out in case of t prime, right? This is what I have explained to you in details in the previous video. If you haven't watched that, please check that out first and then come back to this video. You will get clarity that stationarity means that any time point that you consider time point t, you consider time point t prime, you consider time point t double prime, any time point you consider, the basic properties in terms of expectation, variance and autocovariance, they will not change. So here you are considering covariance yt prime minus h. So this is exactly same as the covariance of yt minus h. This is exactly the same because the process is completely time invariant, right? The process is completely time invariant. It does not depend on the time point. The properties are the same. So gamma t prime minus h is same as yt minus h. That is exactly equals to gamma h. So we started with gamma h and we land up to gamma minus h. So we can conclude that gamma h is exactly equals to gamma minus h, right? I hope this proof is clear. That is what you wanted to show, that for a stationary process, the autocovariance, if you consider the positive lags and if you consider the negative lags, that will exactly be the same. And we will see how we will apply this to, our questions. Okay. Now the next part of the video is for strong stationarity. What is strong stationarity? Suppose you again start with a process yt, t is from 1 to n, right? So when will you say that this process is strongly stationary? When the joint distribution, if you consider, as of now I haven't talked about the distribution, I have only talked about certain properties, right? When we are discussing weak stationarity, I haven't used the word distribution, but now for strong stationarity, everything will be related to distribution. The joint distribution of yt1, yt2 up till ytk is the same as the joint distribution of yt1 plus h, yt2 plus h, ytk plus h. And this is the definition of strong stationarity. So as I was telling you, that for weak stationarity, when I have written the definition, haven't mentioned anything related to the distribution. I have only mentioned these three properties: expectation, variance and autocovariance. But for strong stationarity, everything is related to the joint distribution. That is why it is strong. That if the distribution is the same, then the properties will automatically be the same, right? If the distribution is the same, then the properties in it will automatically be the same. So basically what strong stationarity is telling you is that the distribution is time invariant, right? The distribution itself is time invariant. So previously what we were saying is that only the properties, certain properties are time invariant. It can come from any distribution. So this mean variance and autocovariance that we were talking about, this can come from any distribution. You can thought of binomial, it could be Poisson, it can be normal, it could be standard normal, it could be log normal distribution, or it could be uniform distribution. So any distribution that you can talk about, you can think of any distribution. For any distribution, if these properties are same, you will call it weak stationary, right? So this random sample, that this time series, these values can come from any distribution, but if the properties are the same, you will say that the process is weak stationary. But here, mandatorily, what you need is that the distribution, the joint distribution also has to be the same. This is the strict condition that you have to follow for strong stationarity by t plus 1, t plus 2, t plus k. So these were the original time points, right? T1, T2, Tk. But if you increase them by some lag value h, right? If you increase them by some lag value h, then also you will see the distribution, the joint distribution is the same. The joint distribution is the same. So basically what you are saying here is that this yt1, yt2, ytk is exactly equals to the joint distribution of this yt plus t1 plus h, yt2 plus h, so on, ytk plus h, right? The joint distribution is the same for this time point and for the lag values of this time points, right? So this is basically invariant, time invariant. If you shift the time origin, then also the distribution is the same. And if the distribution is the same, then the properties are bound to be the same, right? If the distribution is same, the properties are bound to be same. So for more explanation, you can understand this in this way. Suppose you are considering two time points, t1 plus h, t1 and t1 plus h, right? So if you want to show a time series to be weak stationary or covariant stationary, what you will say? You will say that expected value of t. Okay. Oh. So expected value of y at period t1 is exactly equals to expected value of y at period t1 plus h. Right? This is one of the properties. Again, variance of y t1 is exactly equals to variance of y t1 plus h. Right? And the autocovariance of y t1 and y t1 plus h is exactly equals to covariance of yt1 plus h and t1, sorry, yeah. So t1 plus h minus h, so it is only yt1. So for covariance or weak stationary, you have to show this thing for these two time points, right? Expectation same, variance same, and the autocovariance is also same. There is no distributional assumption. There is no distributional assumption. That is the important thing. But similarly, if you want to show it for the strong stationary time series, what you will say, if yt1, yt2, the joint distribution of these two things has to be exactly equals to yt1 plus h, yt2 plus h. If you can show these joint distributions are same, then automatically these properties will also be the same, right? If you can show that joint distribution is same, because from the distribution you derive these properties, right? But here we are only considering the properties, no distribution. But if you say that the distribution itself are the same, the properties are bound to be the same. So what we can conclude from the above discussion is this. This is the very important thing that you must know, that strong stationarity implies weak stationarity, but the reverse is not true. From the discussion, it is very clear that strong stationarity means the distribution are the same. If the distribution are the same, the properties are also the same. And if properties are the same, it directly implies the weak stationarity. So if a distribution of process is strong stationary, it automatically becomes weak stationary. But weak stationarity does not always imply strong stationarity, because we don't know the distribution is same or not, right? So you can consider this as a Venn diagram. So here you have strong stationary and here you have weak stationary, right? Weak stationary processes are a subset of the strong stationary processes. If the distribution is same, you have this strong stationary, and inside, for those stationary process, Strong stationary process for whom the properties are the same, these are the weak. Weak is a subset of the strong. Not all weak is strong, right? I hope you got this. Okay, so with this we have finished the types of stationarity. Now for your clarification, I have given you this question. Let us solve this question together. That will solve all your doubts if you have any. So this is a process. Yt is 0.5 yt minus 1 plus epsilon t, where this epsilon t follows IID normal 0 sigma square. Now you have to show that this process is covariant stationary, or it could be, the question could be framed like it is stationary. Prove that this is stationary, or show that, check that it is stationary or not. So whatever it means, you have to show that it is covariant stationary or not. So for that, again, if you have seen my previous video, you know how to, use the lag operator. If you haven't watched, then please watch my playlist on time series. You will know how to apply this in this processes. I have explained you earlier. So this is yt, right? Lag of yt. So simply lag of yt is yt minus 1. Lag square yt is basically yt minus 2, and so on and so forth, right? So here yt minus 1. So the degree of this will be the lag here. Degree of this lag operator is the lag you see here, and plus epsilon t, right? So what you can do, you can take this on the left hand side, epsilon t, and then you can take yt common. So you have 1 here and minus L here, epsilon t. So next, what you will do, assuming assuming yt is invertible. Assuming yt is invertible, I will come to invertibility in some later video. What you can write, 1 minus 0.5 L inverse into epsilon t, right? So I have taken this expression on this side, right? And now you can expand this, L plus 0.5 square L square plus so on, right? It will continue like this into epsilon t, because as you all know that 1 minus x inverse is 1 plus x square plus x cube plus so on and so forth. So here x is basically x is 0.5 L, right? So I have replaced x by 0.5 L and you get this. So what you can write, yt is epsilon t plus 0.5 epsilon t minus 1 plus 0.5 square epsilon t minus 2, and so on and so forth, right? This is what you have from here. Epsilon t, 0.5 epsilon t minus 1, 0.5 square epsilon t minus 2, so on. So it is an infinite series. So you have converted. So whenever I have told you this rule, that whenever you have this, yt is dependent on yt minus 1, you have to convert everything in terms of epsilon t's, right? Why this is so? Because we simply know the distribution of epsilon t. So for any calculation, you have to convert this process yt in terms of epsilon t, and that is what you have done here. So everything here is epsilon t in terms of epsilon t, and you know the property of epsilon t. So you can check stationarity from here simply. What is expected value of yt? So expectation will be on everything. 0.5 expected value of epsilon t minus 1, and so on and so forth. Now you know that this is 0, this is 0, right? From this thing, it follows normal 0 sigma square, and for every time point, right? For all t. So here for t minus 1, t minus 2, everything will be 0. The expectation is 0, which is a constant, right? Okay. Then you have variance of yt. Variance is simply variance of epsilon t plus 0.5 square, this, right? 0.5 square variance of epsilon t minus 1 plus 0.5 to the power 4. This will be squared again. Then variance of epsilon t minus 2, and so on and so forth, right? So again, I have to write the property variance of ax plus by. So what is this? This is a squared variance of x plus b square variance of y plus 2ab covariance of xy, right? This is the formula that I am using here. Now since covariances are all 0 because epsilon t's are IID, this is given to you IID. Again, if you don't know the concept of IID, you can watch my videos. So the covariance has to be 0. There is no autocorrelation. Epsilon t's are independent and they are identically distributed. So these covariance terms are all 0. So just simply a squared variance of x, b squared variance of y. You are using this for every term. You can expand this to many terms also, x plus b, y plus c, z and so on. So formula will remain the same. And now what is the value? This is sigma square from here, normal 0 sigma square, right? So now you have 0.5 square sigma square plus 0.5 to the power 4 sigma square and so on. Simply take sigma square common, so you have 0.5 square plus 0.5 to the power 4 so on sigma square, and this is, if you know this formula, this will be simply this, right? This is an infinite series and you can sum this in this way, right? A r square. So this is GP series, basically infinite GP series. Sum of infinite GP is written as this when the r is less than 1. So here what you have, sigma square 1 minus 0.25, right? So sigma square upon 0.75. So this will be your variance, right? Variance of yt is sigma square by 0.75. This is also independent of t. So your mean is also constant, which is 0, which is independent of t, and your variance is also independent of t, depends on sigma square, which is a constant, upon a scalar quantity. Now all you need to do, show this for covariance, right? Autocovariance, yt minus h. So write the previous expression, this 0.5 yt minus 1 plus epsilon t, and here you have 0.5 y t minus h minus 1 plus epsilon t minus h, right? Okay, now this you all know, for h equals to 0, this is simply will be the variance of yt that we have found out here. I am not writing it again. What happens for y h equals to 1? So it is covariance of yt and yt minus 1. So simply instead of h you are writing 1, right? So from here what you will have, this will be intact, and here you will have 0.5 yt minus 2. So here you are putting 1 plus epsilon t minus 1. Now if you look carefully, you don't have any common term, so time points are not matching, right? The time points are not matching. Why? Here you have yt minus 1, here you have yt minus 2, here you have t, here you have t minus 1. So what will be the covariance? It is simply 0. So how do you find out covariance? You take pairwise covariances, right? Covariance of this term and this term, then this term and this term, then this term, this term, this term, this term. So basically you combine every term with every other term pairwise, right? But if you see covariance of 0.5 yt minus 1 and covariance of 0.5 yt minus 2, this is simply 0. Yt minus 1 and yt minus 2, it has no correlation. Again, epsilon t minus 1, they are independent, no correlation. Epsilon t minus 1 has no correlation with yt minus 1 has no correlation with this, and this also has no correlation with this. So everything, if the coefficients are, if the time points are matching, then you can find out in terms of variance, right? But here there is no common time point, so the covariance is simply 0. And as in when you go on doing this for t minus 2, for for h equals to 2, for h equals to 3, all the covariances will come out to be 0. You can do this for yourself. This can be your homework. So do it for 1 or 2 more lag values and you will see that every covariance term will come out to be 0. So what is the autocovariance here? Autocovariance is sigma square by 0.75 when h equals to 0, that we found here, right? When h equals to 0, this is simply variance of variance of yt, which is this, independent of t, and it is 0 when h is not equals to 0. When h is not equals to 0. So for every other values, every other lag other than 0, the autocovariance will come out to be 0. So what you can say from here is that autocovariance is also independent of t, right? I hope this is clear. So we have successfully shown that expectation is independent of t, the variance is independent of t, and here we showed that the autocovariance is also independent of t for all h, when h is not equals to 0 and for when h equals to 0. So what does this mean? It basically means yt is covariant stationary, right? So in this way you have to check stationarity for a process. I hope you like this video and you get some lessons from it. If you have any doubts, any questions, you can ask me in the comment section, and if you like this video, give me a thumbs up and don't forget to subscribe to this channel, an Economist. I am making these PPTs with a lot of attention and hard work so that I can make things clear for you. So give me a thumbs up and do subscribe to this channel. This gives me immense motivation to go on. And thank you for your time. And in the next lecture, I'll be coming with some special covariant stationary processes, and we will go into this one by one. So stay tuned for the next video, and see you next time. Thank you for your time.